Hi, and welcome to part 2 of your nervous system screencasts. We left off where you were working on this nervous system practice worksheet. We had learned about the basic structures and functions of the nervous system. We reviewed a neural circuit, the types of neurons, as well as identifying the major structures that you find within a neuron. And when we were describing those major structures of a neuron, often we were referring to the direction that an impulse travels down a neuron. They always enter through the dendrite, arrive to the cell body, travel down the axon, and exit the axon terminals. But what's going on with that impulse? How is that actually happening? That's what we're going to talk about now. So some background info that you're going to need to know in order to understand how a nerve impulse works. First of all, we're going to hit some vocab. Resting potential, also known as membrane potential, this is the difference in an electrical charge across a membrane. So we're talking about negative versus positive charge. Next up, action potential. So sometimes people use impulses and action potential interchangeably, but there's a slight little nuance to the difference. So an action potential is when the electrical charge across that membrane, so on either side of a cell membrane, so we're talking about a neuron's cell membrane, that electrical charge is suddenly flipped. So if we start with negative inside and positive outside, now all of a sudden it's negative outside and positive inside. That's what an action potential is. A sodium-potassium pump is a specific type of protein. We actually learned a little bit about it when we were talking about cell transport, and it actively transports, so we're moving against the concentration gradient or up the concentration gradient. It's transporting sodium ions, that's represented by Na+, out of the cell, and we're talking about a neuron, and potassium ions represented by K+, they're pumped against their concentration gradient into the cell. And last, voltage-gated protein channels, and that should actually have a little dash between it like the sodium-potassium pump does. So voltage-gated protein channels, again, another type of protein that you find within a cell membrane, and again, the cell membrane we're talking about is that of a neuron. And those are special protein channels that only allow materials in and out when they are activated by the changes in membrane potential and changes in that charge. So here's an example of a sodium-potassium pump doing its job. So again, we have this cell membrane. You can see it's a phospholipid bilayer, and we have this protein. And we have ATP because it's actively transporting these sodium ions. So it needs that energy to pump them against the concentration gradient. So we have those 3 sodium ions. We have ATP. We use that energy to pump the sodium out of the cell. And then at the same time, we have the 2 potassium ions being pumped into the cell. Then I also have an image here of the voltage-gated protein channel. Pretty simple. Without a stimulus, that protein channel remains closed, so that it won't transport those materials in and out. But with that stimulus, that change in membrane potential occurring, that protein channel is now open and it can now exchange those materials in and out of the cell. Okay, so let's walk through the steps of activating an action potential in a neuron. So first of all, we have these sodium-potassium pumps. Actually, before I get there, I want to point this out to you. You're going to see 2 structures this whole time as we go through these steps. You're going to see this graph. So we're talking about the internal neuron potential. So we're measuring this in millivolts. It's a voltage. So here's -70. That's a general measurement or average measurement of the resting potential inside of a neuron. And when I say it's at rest, it's inactive. It's not transmitting an impulse. And then we have time across our x-axis. Down here, we're showing a segment of an axon. So it's a very long tube. Outside of the cell is out in this space. And then we have inside of the cell in here. All right. You will see these 2 figures as we move forward through these steps. So jumping back into the process here. It says sodium potassium pumps in the membrane, as we saw in the figure on the last slide. They pump 3 sodium ions out of the cell for every 2 potassium ions that they pump into the cell. As a result of that uneven pumping of these charged molecules, because they're both ions, we end up with the inside of the cell having a negative charge with respect to the exterior. That is because we have more of those positively charged ions outside of the cell than we do compared to the inside of the cell. So again, even though they both have pluses, those ions, it both looks like they're positively charged ions. Because there's more positively charged ions on the outside, that would make the inside negative in respect to the outside, or with respect to the outside. So this is just resting. This is just a neuron just hanging out. Again, positive outside, negative inside. We're resting inside here, again at like negative 70 millivolts, just like we referenced. Negative on the inside, negative measurement. All right, so step 2 is called depolarization. Oh, I also want to point out to you here, it says neuron is inactive and polarized. So polarized, so we have those different charges. Okay, so step 2, depolarization. So something's happened here. Something has changed. We have reached a threshold stimulus. Now, neurons are all or nothing. They have to reach a particular threshold, particular stimulus in order for an impulse, in order for an action potential to actually occur, in order for an impulse to travel down that cell membrane. And that is just that stimulus. So once that threshold stimulus is reached, voltage-gated sodium ion protein channels open up in the membrane. Remember from our background information, the voltage-gated protein channels need to have some sort of stimulus in order for them to open up and allow the materials that they transport to move in and out of the cell. So that stimulus allows for the voltage-gated sodium ion protein channels to open up. And sodium ions are pumped inwards. So we're depolarizing the membrane. And I want to point out to you over here, it says sodium ion channels open. However, the potassium ion channels remain closed. So now we have all these positively charged sodium ions that were outside of the cell because they were pumped out via the sodium-potassium pump, but now, since their voltage-gated protein channels have opened, they rush into the cell along with that threshold stimulus. So before that stimulus, we still have that positive, negative, positive pattern that we saw during rest. And after that threshold stimulus, where we haven't reached it quite yet, or before it, I guess, still positive, negative, positive, because we have that unequal distribution. However, check this out. Now we have negative on the outside and positive on the inside. So you can see our graph shooting right up here. We're moving past this 0 mark, past this negative millivolt measurement at resting potential. We are depolarizing this structure. Depolarizing the membrane. Again, inside of the cell versus outside of the cell. Okay, so the next 2 steps, steps 3 and 4, repolarization and hyperpolarization. So let me bring these little illustrations up here. Now we flip-flop. So this is after that threshold stimulus has passed. So imagine it's all the way down here, okay? Afterwards, those voltage-gated potassium protein channels open back up. And at this point, the sodium ion channels have now closed. So we've hit this maximum peak of action potential, the last step at step 2 where depolarization occurred. Remember, an action potential is that reversal of charge in the membrane potential, which we saw. Instead of having, I'm going to jump back a slide, instead of having negative on the inside and positive on the outside, we had a reversal of charges. Here's our action potential traveling down the membrane. Okay, so we did that. However, now we got to repolarize the membrane so that we can get back to resting potential. Once those potassium ion protein channels, the voltage gated ones, open back up, potassium is pumped back outwards and we balance and we repolarize the membrane. Now there's also this little part here. I want you to notice that it's not a perfect bell curve. It actually dips beneath our resting potential. This is called hyperpolarization. Hyper meaning, oh sorry, went back for a sec, guys. Okay, hyper meaning above or like beyond. So we've gone beyond our state of polarization at resting potential, and we've actually moved a little bit more deeply into that negative millivoltage. At hyperpolarization, membranes can actually no longer generate action potentials. This is just a temporary state, and that's why like our neuron doesn't remain like constantly fired once the threshold hits, that threshold stimulus hits. It's a temporary reversal of charge as that threshold travels down the membrane, but then it's shut down immediately right behind it. So I really love this little cycle that we see here. It shows you those four major steps of resting potential, depolarization, repolarization, and hyperpolarization. And it also shows you where on the graph that's occurring and what's going on with those sodium and potassium voltage gated channels. You also might have noticed as I was going through the slides, it said CC down in the corner, and then it gave you a particular time to watch. Those, if we were in class together, we would be watching these little segments of this video, this crash course. It's called Crash Course Part 2, Action Potential. If you follow this bit.ly link, you can watch the whole video. Crash Course talks a little bit fast, so it might be a little bit speedy, but I think he does a great job of explaining it. And just as a reminder, bit.lys are case sensitive, so you'll type 3 capital U, 3 lowercase a, capital Q, capital V. Here's a quick C for you. I'd love for you to practice this graph. I want you to first, well, of course you can use these word bank options, but what you're going to do first is match the correct steps of generating an action potential to each blue number on this graph. Notice there are 2 5s, so they'll both have the same answer. And then there are a few descriptions that you can place around the graph. If you press pause, then you can do practice all on your own, and then you can press play to see the answers pop up for you. Okay, so here are descriptions showing where sodium ions are heading in to the cell, so we're heading into the axon, and at this point on the opposite side of the graph, potassium ions are heading out. Step 1 is the threshold stimulus. Remember I told you it's an all or nothing thing. So you have to reach that threshold stimulus in order for this whole thing to occur. So I like that this graph actually shows failed initiations. So there was some sort of stimulus here. However, the threshold stimulus, they just didn't get to it. So like an analogy would be like you're going to a store, you have $20 or you have $10 to buy a shirt that you want, but the shirt is $50. You're not going to be able to buy the shirt either of those times unless you come in with $50, and then you get it. So that's the threshold stimulus. We have depolarization first with those sodium ions rushing in. We're going to flip the charge of the membrane. That's going to generate the action potential, that temporary reversal of charges internally and externally. Step 3, repolarization. Those potassium ions heading out. Then hyperpolarization is a little bit more pronounced on this particular graph. And then back to our resting state. All right, I'm going to pause here. The next thing we're going to do is investigate what exactly happens at the synapse once or after the axon terminals, once that action potential has made its way all the way down the neuron. See you then.